Well, thank you all for being here. Thanks for having me here. A special thanks to Professor Sahar Padinsky for the invitation. I think he's not here right now. Well, for the next approximately 20 minutes, I will be presenting you our recent work about studying the resistive switching behavior from the energy point of view. Well, for those who went to the ISCAS conference last week, you probably listened to the same material. It was a late break news executive paper presented by Professor Sirakoulis. I just wanted to acknowledge the help and support with all my colleagues from Chile, Greece, and Catalonia in Spain. So, I'll start with a quite long introduction just to present to you our way of thinking in this work. Well, first of all, we have the commonly observed, well, I don't have a laser pointer. I don't know, this is not working. Anyway, well, as we can see here, there are two commonly observed IV types about resistive switching devices, the bipolar and unipolar ones. It works now? Thanks. Okay, independently, or okay, we can see here, depending on whether both polarities or one polarity are required in order to switch our devices, to set and reset them. Independently of that, both of these types of devices demonstrate huge variability, which is quite of a problem until now in this kind of technology. This variability concerns both the so-called threshold voltages, which are the voltages, as you can imagine, that once we exceed them, the applied pulse, then we can apparently see the resistive switching event. And these threshold voltages are not hard thresholds, but alternatively, they demonstrate, they range, they vary around the mean value. They normally demonstrate, to the best of my knowledge, a normal distribution. And on the other hand, we have variability in the final resistive states, the on and off states, the final resistance when our device ends up after the set and reset process. So from these two categories, let's stay on this one. I will get back to this later. Another classification concerns the internal resistive switching mechanism, whether it is, let's say, interfacial or filamentary switching. I'm not a device expert in order to explain these things perfectly, but as an engineer, as an end user, one can easily recognize that up here, we have a device which is more easily configured in intermediate resistive states. Okay, by increasing the amplitude of the applied pulse, one can more easily tune this device in an analog manner, both in the set and the reset process. On the other side, we have devices that almost never change their state unless we exceed a certain threshold, okay, both for the set and the reset. So we can see this sudden jump in the current and nothing in between. There's no intermediate states. So moving on, what's more, the resistive switching devices demonstrate a stochastic nature. What does it mean, stochastic? It means that even if we apply a voltage of amplitude much less than any threshold, any observed threshold, but wait long enough, eventually we will see a resistive switching event. Okay. This was very well presented by a group of Wei Lu back in 2009 in this paper. So they presented the characteristic wait time, the average wait time, the average time one has to wait until he sees probably a resistive switching event, a sudden jump like this one's in the IV characteristic. And of course, the more close the applied amplitude gets to the so-called threshold, the higher the probability to see the switch and the less the wait time. So this, the nature, the existence of the threshold voltage, and which varies, okay, and combines well with the so-called second memristive fingerprint. what does this say? It says that, well, you might all remember that in this kind of IV plots, once we increase the frequency of the applied periodic pulse, but we keep the amplitude fixed, the hysteresis plot starts to shrink, so these lobes shrink. We eventually do not have any hysteresis at all for high enough frequencies. But if we keep the same high frequency and increase the amplitude, then we see switching again. Okay, so we have, apparently there are some thresholds, there are switching thresholds, okay? But what happens here? Here they suddenly disappear, depending on the way, on the type of the applied pulse, and we don't have resistive switching, and then if we apply a higher amplitude, we suddenly see resistive switching again. So we have thresholds, okay? These thresholds are not hard thresholds, but they demonstrate variability, a normal distribution, which also moves higher depending on the frequency of the applied pulse. This was shown in a work by a few colleagues of mine in Universidad Autónoma de Barcelona. And they showed experimentally in unipolar hafnium-based devices that the set and reset thresholds, they increased with the voltage ramp speed. They increased, in other words, with the frequency of the applied pulse. Okay? The higher, the shorter the rise time of the pulse, the higher the amplitude required to see eventually resistive switching. So there's too much of information for those who do modeling of resistive switching devices, okay? And perhaps it's the reason why most of the modeling solutions so far, modeling approaches, have remained behavioral solutions, and they don't have much information about physics, and they have probably a switching rate which is higher above the threshold and shorter below the threshold, okay? But we have seen that these thresholds exist but not exist, and this is because they depend on the biasing conditions. But is there any relevant magnitude independent of the biasing conditions which determines the set and reset process? And apparently it is. In the same work, it was shown that the average energy injected to the device stays in the same order of magnitude for the set and the reset, and this is independent of the biasing condition. Okay, here we increase the voltage ramp speed, we shorten the time, the rise time of the applied ramp voltage, and we measure the same average energy required. So in this work, after this long introduction, what we did, and I will show you, is that we explored experimentally the set and reset behavior of resistive switching devices from the energy point of view. Okay, I will show you some statistical analysis of the total energy required concerning both unipolar and bipolar devices. These were totally characterized by my colleagues in Barcelona. We did only the statistical analysis. I will explain the criteria we used for the resistive switching and the energy calculation. I will show you our approach then, which concerns fitting a distribution to the energy histograms, the definition of the probability of a resistive switching event for a certain energy level. And regarding the study and extraction of universal parameters, I will present you what we think is a first step towards the definition of key performance parameters for this new and emerging technology, and the first order approximation, a simple approximation, design-oriented model suggested for both binary and analog operation of resistive switching devices. Well, first, regarding unipolar devices, since we have this abrupt change, this jump in the conducting current, well, now from our measurements, we have time, voltage, and current, right? So here is the voltage on the device. So in order to define the moment when the resistive switching happens, we search in this plot for the higher point in the voltage graph, okay? So this is the clearest among all the graphs we have. So we measure the energy from the starting point of the experiment until this point. For the reset, here we have no clue, but we can look at the current time plot, and here we similarly will look for the highest point in the current plot, which shows us when the resistive switching happened. Eventually, we put all the analysis together, and in this plot you can see that we were able to reproduce what it was proposed in that paper I showed to you. Apparently the energies employed to trigger resistive switching process are independent of the biasing conditions. You can see right here. So they constitute an intrinsic parameter of the resistive switching mechanism, and for us it is a candidate magnitude for the definition of performance parameters for this technology. Moreover, you can see here that the higher the voltage ramp speed, the more robust the behavior becomes. Here for lower increasing ramps, apparently you give time for different kinds of behavior to occur, but with a perfect square pulse or a very high increasing rise pulse, you can see this kind of behavior. So these data, we put them right here. We create the histograms for the set and reset measured energies, and for each one we fit a distribution function. Then we have the cumulative distribution function, which rises towards 1, probability 1, as we include more and more switching events, which fall right here. And so we have a candidate performance parameter is the probability change per energy unit. How much more probable it becomes to see a binary switch or resistive switching event for any additional energy unit that we inject to the device. And here what we propose is, okay, with all this information, one can know practically how much energy it is required to inject to his devices in order to have a switch, to guarantee a resistive switch. But one can alternatively discard all things and stay with a linear approximation. Okay, a linear approximation, or a higher order, a better approximation for this, which will give us a simple function about the probability to have a switching event depending on the energy we inject to the device. This was for unipolar devices. For bipolar devices, it's a little bit more complicated, more if your device demonstrates a more incremental way of switching. Okay, here you can see, especially for the reset, you have an incremental change. So here one has to define what it means, a resistive switching event. When did his device switch? Okay, one can set certain resistance limits, or can say, okay, since this depends on the initial memristance, one can say, okay, I will consider my device switched when the memristance becomes 10 times larger, or 1/10 of the initial memristance. I just want to say that one has to define some criteria about when the resistive switching event happened. So using the same recipe, you can see here several plots, energy histograms for bipolar devices, 50 cycles each. We increase the current limiting. So you can see that there are distributions that fit quite well to all this kind of data, or most of it. It's more stable for higher limiting currents. The recipe is the same. Then we have a cumulative probability distribution function, and we can follow the same linear approximation to have a simple equation for the energy required to have a resistive switching event. Well, that was for binary operation, but we can also explore the incremental behavior. I mean, okay, we can define a criteria for a binary switching, but we can also see what happens in between, okay? During this transition, we saw that apparently there is a parameter which seems to be uniform for all devices, and this is the resistance change per energy unit, okay? The rate of change of my devices for every additional energy injected to the devices. You can see here the performance parameter analysis. Okay, we have some classification here of resistance change rates per energy, and we can see that these data, they gather together around a mean value. Okay, these were results from 150 set cycles of these bipolar devices, which means that we can use this information in order to have, again, a linear or a higher order approximation of this behavior and have a simple function which will give me I can use in order to have to predict the intermediate resistance where my device will most probably stay for a certain energy level injected. So what we did, in short, okay, regarding this study and extraction of parameters, we made, as I said, we think the first step towards the definition of key performance parameters for this technology that still do not exist. We defined the probability for resistive switching event for a certain energy level. We also proposed the first order really simple approximation, a design-oriented model for both binary or analog operation of our devices. This is nothing more than a simple way to estimate when a memristor will switch or not, depending on the switching criteria we set. And through this approach, we are able to answer questions fully or partially, such as how much energy the resistive switching events require, okay, or what is the quantitative effect of the energy on resistance of my device. So I will end up with application of this approach regarding a complementary resistive switch, which is nothing more than two memristors in series with opposite polarities. This is the same configuration of a NOR logic gate, binary logic gate, within the MRL design scheme proposed by Sahar a couple of years ago. Well, in this scheme, I will not explain how it happened, it works, but we have 4 different input combinations. We can have 4 different initializations of our devices, are on, are off, etc. So here we examined only, there are only 6 cases here where at least one device switches state, okay? 3 of them are repeated, so we examined only these 3 cases. And in this experiment, we used 2 known devices, 2 real memristors. We considered binary operation, okay, not multi-state operation or analog operation. We set specific resistance limits where we consider that our device switched or not. For every combination here, we have 10 different measurements averaged. I will show you how these devices operate here. This is the applied pulse. Okay, we have a resistor in series to limit the current going through the devices. So you can see here the dashed lines are the limiting resistances for the set and the reset process. We live in between a resistance gap as a guard band, which we think is a good way to have limits for the resistance for the set and the reset process. You can see here that the measured energies are similar. I mean, the same. It's the same trend, and the faster here what we do is practically it's a square pulse, but we change the rise time, and you can see that the faster the rise time, the better this distinction it gets. So with this methodology, we measured we show here the energy with time during the experiment, having 2 memristors in series with opposite polarities, and here the measured energy with time. This dashed line here and here, the purple and the green ones, show the limits that our first order approximation give us, which means that if you inject this energy, it will guarantee you a resistive switching event, right? So here you see how one device switches to on. These are 10 experiments, I think. The other one remains in RF. We have 1 kilo ohm right here and 100 ohms right here. And another case, the more complicated one, where both devices switch in a reciprocal way. Their initial configuration is exactly the opposite than the final one. So they start from on-off and they end up in off-on, okay? And here you can see that these points, green points, are the moments when the resistive switching occurred. So you can see that all these energies required are below this threshold, which seems that this first order approximation works quite well. And also it happens quite well for these 2 devices in series, which is a more complex configuration, and except this one, which slightly exceeded this approximation, let's say, limit, but this model worked quite well. And what we propose is that the energy, the injected energy required to cause a resistive switching event to be perhaps the origin while modeling, while creating models for resistive switching devices. So I will just, before thanking you, I will just acknowledge the support from the KNOP company and the Spanish ICTS network micro nanofabs. Well, thank you all for your attention.